Okay, welcome everyone. Today I'm going to give a talk or recording a talk that I actually gave because usually it's like someone like easier to just record the talk in my usual environment here instead of just in the wild. And so the disadvantage is obviously that there will be no feedback from the audience, but we'll survive. So the talk is essentially about an idea, which I'm getting obsessed by more and more and more, is how to apply artificial intelligence to mathematics. The whole point for me is the following. So artificial intelligence, in what form ever, let's not be too picky here, is roughly around since the 1950s, 1960s, and came out of mathematics essentially. But nowadays, it's mostly used. It got very, very popular in the last like 10 or 15 years, mostly due to computational advances. But anyway, came from mathematics or computer science, which around in the 50s and 60s was roughly the same anyway. Maybe it's still the same nowadays. I'll leave that one to you. But anyway, it came out of mathematics. And nowadays, I'm sitting here and I'm designing an exam. I'm a mathematician and I'm designing an exam myself. What on earth is going on? Right? The big banks use artificial intelligence, retailers, the technology firms. On your iPhone, there are probably like a zillions of different applications that run with artificial intelligence, and it came out of mathematics, and I'm not using it. That just can't be right, right? That's just something is going wrong here. In particular, if we just think about it, what am I really doing? Well, I'm writing exams myself and I'm grading exams myself. What on earth? I'm very unfair. I'm completely an unfair person. It would be much fairer for everyone if it just the machine would design the exam and the machine would do the grading, automated grading, automated exam design. And similarly, automated paper writing, automated theorem proving, conjecturing, and whatever. The machine eventually will be able to do that, and there are some ideas in that direction. It just takes a long time. But somehow I don't think that's really a problem. If you just think about human evolution, well, taking place over 100,000 years or something. I'm really not good with biology, so don't blame me here on the numbers. Over a long time, and artificial intelligence that started in the 50s, I think it's actually in a pretty good state. And in 1,000 years or whatever, God knows. So there's this saying in artificial intelligence that eventually AI will look back on us like we look back on fossils nowadays. So who knows? In particular, again, me as a mathematician, my real goal should be I'm kind of a failure as a human being, and every human being is somehow not perfect. The machine is much better. So my point of doing mathematics should be to replace myself. Right? So you don't want to hire me, you want to hire a machine doing my job. We're quite far away from that. Or maybe not actually, because everything is somehow growing exponentially fast. But anyway, right now, when I'm recording this in 2024, there is no automated exam generation or automated exams, computer generated exams, as far as I know. Automated grading actually already happens, but not to a degree that I would like it to happen. And automated paper writing is in 2024 a little bit uh, of a no-go topic. So it's usually a little bit controversial, but eventually theorems in mathematics should be just done by computer. So what is the point of this talk now? Well, the point of this talk is not to explain all of that. So maybe eventually, as I say, I'm evolving a bit. Maybe eventually we'll do more things about how to apply really AI in mathematics. The point of this talk is more like explaining the mathematics of AI, just kind of not quite what I want, but it's kind of the introductory lecture. And it turns out that, well, it's actually a really, really, really simple idea. So if you know a little bit of linear algebra and a little bit of calculus, you're already good to go into the wild and do your own AI type of machine learning or deep learning or whatever type of problems. Because essentially it's all about, well, we'll kind of explain more details about matrix multiplications if you want. And this whole idea of learning that I have in mind, or maybe not I have in mind, but my picture of how AI learning works and maybe learning in general is this forward loss backward, forward loss backward, forward loss backward. We'll see that several times. Forward loss backward. And yeah, so I really have this idea of just, well, again, not I have the idea, but the idea is essentially that learning should be a forward. then you get a loss, and then you do it backward, and then you have this little loop, and you just repeat it and repeat it and repeat it and repeat it. Really, just practice makes perfect. That's true for humans, and that's true for AI, because essentially AI should be designed on humans anyway. So, and I'm trying to explain like the mathematics behind it in a language that a mathematician would be able to appreciate it. I hope. At least I do appreciate it this way. So that's a kind of a trillion really brilliant introductions to machine learning and friends, but they're usually not written for mathematicians, and that's kind of fine. So they usually. So I recently watched a really beautiful uh, kind of guide how to do artificial intelligence yourself, and they spend a long time on explaining matrix multiplication because, of course, matrix multiplication is not something everyone knows. But as a mathematician, I feel like those 2 hours explaining matrix multiplication was a little bit like a waste of time for me. I would have liked to see more details on things I'm not so aware of. So maybe we just think of this as being an introduction to kind of AI from a mathematical point of view. Okay, so let me just get going. So what I want you like to have you in mind is the following type of question. Identify handwritten digits. That's like a really classical question. Yeah, let a machine identify handwritten digits, and here could be something like this, like simple like this. And how do we make this a mathematical problem? Well, what we do is we convert, let's say we have pictures of handwritten digits, and we convert them into some, let's say, grayscale 28 by 28 grid of numbers, where really just the number itself, whatever, 80% gray, something like that, 0.8, 80% gray, something like that, and you have 28 by 28 as an example. Could be anything. But that is really just a vector if you just flatten it out. Instead of having 28 by 28, you just flatten it out into a 784, if I haven't done my calculations wrong here, kind of entry vector. And what would be the output? Well, the output would be a 10 entry vector just for every, just like a probability for every of my possibilities here. We'll see an example in a second. So essentially what we have, this problem, if you want, is just a function. We're trying to find function from a 700 whatever dimensional space to a 10-dimensional space. We're trying to find that function actually. And that function is handwritten digits, handwritten digit function. So here's an illustration that I stole from 3Blue 1Brown. Has a really beautiful series on machine learning or neural networks. And really, this is just what it is. Here's an input. This is a picture of a number 3 in some grayscale thing. And here are the grayscale values. So 1.0 is like very white, 0 is black, and whatever, something in between is gray. And it's just an input image, in this case really 28 by 28, that I just flatten out in one vector, 784, that's it. Just by taking first row, black on black doesn't work all that well. Let's try white on black. Just first row, second row, third row, whatever, and just put them all together in one line into a vector. So that would be an input example here. And an output example is something like here below. So some list of numbers, 10 of them, and each one of them is kind of a probability for whatever to be whatever. In this example here, like 60% certainty that the number that I feed it in, or the example I feed it in, is a 3. Now that's kind of the idea I have in mind, where essentially all kind of type of learning processes are somewhat a function from a space to a space. And that's something like mathematicians like, functions from spaces to spaces. To be realistic here, what we all do, what we all learn very early on, like in calculus or whatever, functions are very important. Yeah. So here's an example of how you could apply functions to have some learning tasks to identify handwritten digits. You can do the same with any type of kind of. You just need to put your data into some vector form, and you have a function from some space to some space. Usually, maybe I should say that, and I will kind of say that several times. Usually, the function spaces are really large, so that's where the completion part of the computational complexity comes in. Like in this case, it's quite a large space already, right? Anyway, so let's essentially rephrase our task. We have a function. How can we describe that function? It won't be an easy function, so kind of the mistake, in quotation marks, a lot of younger people do is that they think a function is something given by a nice formula. But honestly, most functions are not given by a nice formula. And that's essentially the problem we're running into. Think about predicting the weather. That's a function which is hopelessly complicated in some sense. It's not given by any nice formula. So how can we describe that function? We are certainly not hoping to write down a nice formula for that function. So the whole point of kind of the mathematics of AI, if you want, the mathematics of machine learning, is to describe a highly complicated function on a really large space. That's what we want. We want to describe that in the sense that we want to have something and we feed it in and we get something out. Again, like with the weather example, keep that in mind. What we should expect is not an easy thing like x goes to x squared or something, but something much, much, much more sophisticated, which you probably can only describe approximately, right? So that's probably what's going to happen, which is good enough. That's how the brain works anyway. That's why we all do mistakes. That's why we're all not perfect, because the brain is just doing kind of trying the same. There's trying to approximate something like whatever face recognition. There's some function which it tries to approximate, and yeah, approximations might go wrong. But that's what we're trying to do. We really want to do that, and the way to do it is what usually people call deep learning. I will mix them up all in one go. So artificial intelligence, machine learning, deep learning, not the same, but I will just make them all the same just to make my life easier. Anyway, the point is to try to answer this type of question where you have a really, really complicated function that you can't describe by x goes to x squared, letting a computer just get the function without human interaction. So the computer detects the pattern itself, and that's kind of the main idea of all of this, of point of this artificial intelligence. The computer detects the pattern itself. I will not tell the computer what to do. I will feed the computer with data, and the computer is supposed to pick out the patterns from the data, instead of classical human interactions where you just really give the computer a specific task. No, we do something different. The computer just does everything itself, and the only thing I'm supposed to do, I'm supposed to feed it in data. My exam, for example, the exam example, I could feed in like 1,000 different potential exam questions that were run in the past, together with the overall score, and then I could let the computer decide to put them together into a nice exam, such that it is fair, so the overall score is like on an average level. And no human interactions. I'm not going to design the exam myself because I am an unfair piece of shit. No, let the computer do it. That's kind of the optimal thing, instead of sitting in front of it and kind of typing the exam myself. I hope that makes sense. Everything, the computer is supposed to do it itself. We are not going to force it to do. That's kind of the main idea here. But now what can we do? We have this function, and I already told you that it's probably not of the form x goes to x squared or something easy that you can describe. The function is probably horrible as fuck. So what do you do if you have a horrible as fuck function? Well, you approximate it using some easier function. And turns out that the most efficient approximation is something you somehow rarely learn following the standard curriculum. Namely, you can approximate a function by piecewise linear functions. A really simple idea. So here, some function, like in this picture here, I can draw another one. Some function, it does something, I don't know. And then we just approximate it using some piecewise linear function, something like this. It's a horrible approximation, but anyway, some piecewise linear, where every little piece is linear. So every little piece is a matrix, and then you have some nonlinearity. And you could do that in several ways. Just in this video, I prefer the piecewise linear, which is probably the most popular one at time of recording, 2024, in machine learning, because it's just so simple. You can approximate any function with a piecewise linear function. That's essentially the idea you should keep in mind. So I want to approximate our unknown function in whatever how many variables using some piecewise linear function. Piecewise linear, I said again, really just matrices plus a piecewise linear map. And a neural network, essentially, is just a piecewise linear approximation of that function, consisting of matrices and piecewise linear maps. So we'll see in a second, I'll go into more details when I go to neural networks. The matrix is just a bunch of numbers, and the numbers are the ones we adjust, And a piecewise linear map, so like the little lines here, every line here is a matrix. And then to bring in piecewise linearity, and I will make sure later, the very end, that we understand why we really want that, but maybe it already makes sense here. To bring in piecewise linearity, you usually choose an easy piecewise linear map, and if you just combine everything nicely, you can essentially get all piecewise linear maps. And the most popular choice, it's kind of a fun one, is a ridiculously simple function with a ridiculously complicated name. The rectified linear unit, or in short, ReLU, which is which is really just this function here. Scary name, easy function. It Whenever it takes an input that is negative, it sends it to 0, and it leaves the positive inputs what they are. That's the function. So neural network in the end, so how the brain is supposed to work, if you want, is just a bunch of matrices plus this little ReLU function, so very harmless. And why? Let me just say it again. I will have a much nicer illustration much later. But why is that important? Well, we can approximate, here's my little picture, every function using a piecewise linear function, but approximation with a linear function, which is really just a line in this example, just can't work, right? So linear is not good enough. A piecewise linear is good enough, and that's why we actually do it. The neural network is just a bunch of matrices and a bunch of piecewise linear things, and the usual piecewise linear things is like really easy function. And I should say it again, you might be wondering now, I'm a mathematician, I can also approximate functions using different things, not just piecewise linear. Yeah, so there are various versions of doing it in machine learning. You don't need to use a piecewise linear map. Just, I personally feel like this approximation with piecewise linear functions is kind of a really good analogy to keep in mind because it kind of really makes sense. You could also approximate with higher order polynomials or something. Anyway, just as a side remark here. The point is there are matrices, and a lot of them. We'll see that in a second. Yeah, and then the idea can be really just summarized in the machine learning mantra. Machine learning mantra is forward loss backward, forward loss backward, forward loss backward, forward loss backward. Machine learning mantra. It works as follows. You calculate an approximation. So you start usually just with a function that is does some completely random shit. Yeah, I'm trying to approximate my blue curve here, and I'm doing it with this piecewise linear map, which is like horribly off. That's usually how you start, with random inputs. A baby still needs to learn a lot. Essentially, you should think of the brain of a baby as being something random. It just can't do anything. It's just completely random shit. And similar here, we start with random shit. So we just do that. And then we calculate the so-called loss, which is really just the difference of the random shit we produced compared to the real data. So here, like let's say, really just the difference of our calculate approximation to the real function. And then we pass it backwards. We'll see that later a little bit more precise. We just adjust the function by trying to minimize the loss function. So maybe we just, in our the little green curve here, maybe we put it a little bit closer to the real data. And then we repeat, 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 repeat. That's how humans learn. Like my baby example again, we start with some random shit. And then you just repeat, 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 input and input and input. And eventually we are at well, my brain is not really great. We are at the place where we have your brain, and your brain is essentially really brilliant in doing some like face recognition. Brilliant. The brain is really good at doing that. But it starts with some completely random shit. And it's the same here. We just adjust it in every step a little bit. So the machine learning mentor is essentially do it, just you have something, calculate the difference, try to minimize the function you get, the difference function, by adjusting the original function. And then do it again. And just do it again. And do it again. Practice makes perfect. Just a mantra here, not just of machine learning, but also maybe of learning in general. Okay, let's now jump to what is really a neural network. So what is it really, if you want? A neural network usually is displayed in the following form, and I will explain what it is in a second, but it's usually like large. I just focus on this small example. So there are some neurons, which are just the vertices here of my little graph, and there are some connections, and there are some weights, usually what they're called, which is just the edges of this neural network. And it can be very, very large, can have many layers. So a layer is just a column in this thing. Um, Actually, strictly speaking, a layer is what is in between the columns. I will come back to that later. But right now, a layer is just a column, whatever. Doesn't really matter how you count. And the task is to approximate some unknown function. And we have neurons, and they are really just the main point in the graph. If you know graph theory, the main point of a graph are not the vertices, the main point are the edges. The similar thing is for the neural network. The main point are the edges. Anyway, the vertices are called neurons, and they're just entries of vectors. So here's a 1 by 1 vector, here's a 3 by 1 vector, that's those three guys, and here's a 2 by 1 vector, just those guys. So entries, the neurons are really just vectors. And whatever is in between is a matrix. I will make that more precise in a second, because what eats a vector and gives a vector? A matrix. So this matrix here, M, eats this vector and gives this vector. And the next matrix takes the middle vector and gives the third vector, and so on. And that's essentially what a neural network is. Let me zoom in a little bit in case you have never seen this notation before. Right, so this is just a vector. There's some entry. The input will be given by some entry, like our 28 by 28 grid just flattened out into a vector. And the output is some vector. And in between you have a matrix, and every edge corresponds to an entry in the matrix, which people usually call a weight. Right? So x, w, x, y, W goes from 1 to the first one, X goes whatever. So this is really then, this matrix here is just a 3 by 1 matrix with those corresponding entries. Here maybe a little bit nicer. This should be a 3 by 2 matrix. So A11, for example, takes the first input, returns the first output. A13, a little bit annoying, I hope I got that right, is that matrix multiplication, the matrix convention is kind of opposite to what the neural network would like to do. But anyway, A13 takes the third entry and returns the first entry and so on. And you just write it down as a matrix. Right? So every matrix here just takes the corresponding neurons in the previous layer and returns the neurons in the next layer. And its values are just given by the weights of the edges. And there's also a bias term, really, just in the sense that I will be more precise in a second. That, well, usually the standard linear function is matrix times x plus bias. Kind of fun fact here. I think mathematicians got that wrong in this case. So usually in kind of data science, you have a slightly different language than in math. But in this case, I kind of really are on board with the data scientists, because they would call whatever we'll see this guy here a linear function. So mathematicians call something a linear function if it goes through the origin. But honestly, a line that doesn't go through the origin, like here's the origin, let's say, is still linear, right? So what neuroscientists, data scientists call linear is what mathematicians usually would call affine. But again, I would really side with the data scientists here, because my blue line is still linear, right? So it's really a line, so a slope that gives the matrix, and a bias that gives kind of the offset from the origin. Again, this is usually called affine in mathematics because you're not hitting the origin. But let's be realistic here. This is linear, so let me just call it linear. Anyway, so that's it. It's a neural network. That's it. It's a combination of matrices, just written in a graph form. That's it. So here, for example, a little bit bigger. So you have 3 inputs, 4 outputs, 3, 3, 2, and you have those 4 matrices. Again, that's what I said. Essentially, the neural network is happening in between, so that's why I have 4 matrices here. So here's a matrix, here's a matrix, here's a matrix, and here's a matrix. 4 matrices plus those biases. Again, I'm citing here with the data scientist. When I say matrix, it's actually matrix plus bias. Fine. And the composition is the map. So a neural network is nothing else than a lot of matrix multiplications. And I really mean a lot of matrix multiplications in general on high dimensional spaces. Okay, you might complain, actually, we'll come back to that later. It's not quite right because I just told you about, well, this idea of approximating a function using piecewise linear functions, because the linear one here doesn't work. Yeah, actually what it really is, it's a matrix, and then you apply, for example, ReLU component-wise So ReLU component-wise, so if you have something, a vector like 3, -1, 2, you apply ReLU component-wise. ReLU, by the way, ReLU or ReLU, I'm not quite sure, doesn't really matter. If you apply it component-wise, you get something like that. So then really a neural network is a matrix and one of those guys and a matrix and one of those guys and a matrix and one of those guys. But what we really will learn are the parameters of the matrix. In something, the ReLU is just there to make it nonlinear, to bring in nonlinearities, and doesn't really learn anything. So I usually ignore it. And that's also such an easy function, then it also doesn't contribute too much to the computational complexity. Yeah, so I'm kind of trying to ignore that a little bit and just try to sell the idea that a neural network is just a matrix, a matrix, a matrix, a matrix, a matrix, a matrix, and a lot of them. That's it. That's learning. Learning is a bunch of matrices plus nonlinearities. Just keep that in mind. So here's another picture. So a matrix, so you have A11, A12, and just the subscript is just the layer, and then there's a bias term, right? This is just a notation for an affine matrix. If you want, you just put the bias term, the shift that you do here, and these are the parameters of our neural network. That's what we want to learn. Those parameters are the ones we are going to change successively. And yeah, just do layer by layer by layer by layer. And many layers means a good approximation. Essentially, you should think of the number of layers as being something like in my little picture here, as the number of points where you break it if you want. So of course, if you break it finer and finer and finer, you should get a better approximation onto your function. That's essentially what you should have in mind. Many layers, better approximation, and the whole deep, which sounds really like, which sounds deep. The whole deep from deep learning just means many, a lot of them. So the standard ones, here are some famous examples. ResNet 152, for example, is something that runs some variation of it. I'm pretty sure it's not known, or it's clearly known, but it's not officially kind of public what ChatGPT uses, but something like that. So it's with 152 layers. BGG 19 with 19 layers. Google Lanet with 22 layers. So they usually have many layers, and that's the point of deep. Many equals deep. Many layers, many parameters, good approximation, right? So why many layers mean many parameters? Because every layer is a matrix, if you want, or in between two layers are as a matrix, and matrices have parameters that we want to kind of learn. Okay, kind of fun side fact here, because everything in the end is about computing a lot of them, like a lot of matrix multiplications. You want to be matrix multiplications to be reasonably fast, and a GPU can do that better. A GPU is more specialized; it can do matrix multiplication faster, and that's why a lot of machine learning things actually run on a GPU. If you don't remember anymore what a GPU is, a graphic card, if you want. So gaming has improved AI in some sense. You can do it even more fancy. I'm not an expert on hardware, but you can go much faster even than a GPU, using sometimes what people call a mechanical computer, which is not a CPU anymore. Essentially, what you should think is a CPU is pretty slow but can do a lot. And if you want to go more specialized, then you get faster, but you can essentially, let's say, only do matrix multiplication. But that's just a random side fact that I wanted to mention because random side facts are fun. Cool. So before we jump into some real coding examples, so I coded some example, I copied some code that I will run live for you, to be completely precise. Anyway, before we do that, to really show you how this works in practice, let me just wrap up and tell you essentially exactly what's going on. So matrix multiplication is a forward. But remember that the mantra is forward loss backward. So I still need to explain the rest if you want. But forward is really just this idea of approximating something using matrices and nonlinear maps like the ReLU. Let me just do the example for what people call supervised learning. Supervised just means I give the answers to the machine as well, not just the data. So here, for example, in my number example, I would give it the picture of the number 4, but also I will tell it, oh, by the way, this is the number 4. And that's the only point of supervised. So I'm not doing anything except giving it the correct labeled data. Unsupervised would be, for example, giving it unlabeled data, which you want to do, for example, in a situation where even you don't know what the right answer is, and then the computer can learn the patterns itself. But anyway, let's stay with supervised learning here, where I give it the answers. Really, just as in the example, just a picture of the digit, of the handwritten digit, and its label. Okay, cool. And what you usually do is you have a kind of a large data set, and you really want to have a large data set. So deep learning is most efficient on large data sets, and you split it into like whatever, depends a bit on the problem, but let's say 80% training data and 20% testing data. And why do you do that? Well, everything here mimics kind of the real learning. It's kind of a fun back and forth. So the more well, machine learning mimics usual learning and what the brain does, but at the same time, because it is machine learning is so successful, nobody really knows why. I will comment on that in a second. But nobody, whatever, it's very successful. And at the same time, then you try to learn something about the brain itself, and then you can mimic that again, and then you try to learn. Anyway, so you split it into 80% testing and 20% training, depending on the problem. Doesn't really matter. And why do we do that? Well, it's essentially how we learn as well. How do we train students? We give them exercises, lectures, whatever. That's like the training data. The final exam is like testing data. And upon performance, yeah, so some students need to redo it. We let them into the wild. Yeah? That's how we do it. And that's exactly how you train a model. So you give it training data, well, let it train, you test how it works, and upon performance, it either needs to redo it or you send it into the wild. And kind of the real key difference between a student and or a human, if you want, and a machine is that a human needs whatever semester to redo it, while a machine can just do one can do whatever. I'm not a hardware expert, but like a million operations, probably way more, a million operations per second, and that's kind of why machine learning is so successful. But it's really just mimicking the same. So we train on the training data, we test on the testing data, and then we can let it into the wild and just whatever, let the user upload a handwritten digit and try to identify the handwritten digit. Okay, and then let me repeat the mantra: forward, lost, backward, forward, lost, backward, forward, lost, backward, and of course, repeat. So forward, run the neural network. Just evaluate the function. Neural network is just a function. It's just a bunch of matrices. You get some output. You run it, you get some output. Loss. Calculate the difference between the results and, because I've labeled everything, the answers, it gives me a function, the loss function. And the goal is to minimize that loss function, because the loss function measures for you the difference between the real answers. Why do I use quotation mark? The real answers and the predicted answers. And then change the parameters, that's the backward, trying to minimize the loss function. And then do it forward again. Going all the way backward, do it forward again, and whatever. Just redo, redo, redo. Practice makes perfect. Repeat, 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 repeat. Hope it makes sense. Forward, run the function, calculate the difference. Backward, adjust the parameters of the function. Parameters, I recall, just the entries in the matrices. Forward, run the matrices, calculate the difference. Backward, adjust the parameters of the matrices. It's all doing it by itself. I'm not doing anything. Forward, it runs the loss function itself, it adjusts the parameters. Forward, it runs the loss function itself, it adjusts the parameters, which is kind of the magic of machine learning. It learns it itself. And nobody really knows why this is so efficient, because everything is essentially random. So you just have some random shit and you adjust random shit a little bit and it will work. It's kind of really strange. It's kind of beautiful and strange at the same time. So you really start with random input usually and adjust the random input using a random method, and eventually it kind of will converge to something nice. Just really strange. So whatever, essentially you should think of every kind of layer in the neural network learns a different type of pattern, but that's not really true. It's really just some random noise essentially. But random noise can generate learning is just really fantastic. It's just one of my one of my favorite takeaways of machine learning itself. Anyway, forward is really down to a bunch of matrix multiplication, because our neural network is just a bunch of matrices and biases. Right? That's it. Forward, matrix multiplication. Okay, and then loss. Essentially, we just calculate the difference between the real values and the predictions. And you should think of this giving us some kind of a loss function in the weights, and the loss just high dimensional, because usually you have like billions of weights, one of the really large matrices and many of them. But anyway, it's essentially just a function that you try to minimize. So you start somewhere and you try to find the minimum of the function. That's it. That's what you want to do. You want to try to find the minimum of the loss function. And how do you do that? Well, right up to this point, it was all linear algebra, it was all matrices. If you allow me to ignore the nonlinear functions, it was all linear algebra. And now comes calculus, not too bad. So how do you minimize the function? Well, there's this idea of gradient descent, which really just means you have some function, you're trying to find the minimum, and at each step you just go in the direction of the steepest descent and just do a little tiny step, and then at the next point you calculate it again and go a little bit further, and the next point you calculate it again and go a little bit further, and the next point you calculate it again and go a little bit further. So all of backwards is just you have this large function, this loss function, high dimensional. You have some way to calculate the gradient of that function, which is usually given by some algorithm run in the background. And you then have another algorithm, which is kind of the backward pass, the optimizer. It goes backward in the system and kind of adjusts all weights according to the steepest descent of this gradient descent idea. And then just you get new parameters on your matrices and you just do the whole process again. So start with some parameters, calculate the difference, the loss function, you want to minimize it, and you do it in some kind of form of a gradient descent, just going the road of the steepest descent, and then go backwards and adjust the weights accordingly to go into this direction of the steepest descent. And yeah, that's it. That's learning. It's just really, really mind blowing. Let me just repeat that. Really mind blowing. All of learning is just this idea of having matrices with parameters, so with entries, that you kind of adjust according to this idea of gradient descent by calculating the difference to the loss function. And of course, practice makes perfect. I say it again, repeat, 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 repeat the whole process. And again, it's really crucial to point it out. You start with random things and you adjust rates essentially just going along a random function. So you end up with some random function, but now the random function is well trained and actually can recognize faces or handwritten digits, can drive cars, find patterns in the financial market, or prove theorems for you. It's kind of really exciting. So very simple mathematics in some sense. Matrix multiplication and gradient descent give you such ridiculous results, ridiculously great results. So as the next step, I'm going to show you kind of how to do it in practice yourself. It's actually quite nice. So the point is nowadays you can just do it. My favorite tool is PyTorch. There are certainly different tools, but that's what I'm going to use. Okay, here we are. I'm going to, well, not really show you, but I can show you how to use it yourself. I'm not going through the code. Kind of coding is not so fun to watch, but I can kind of show you how to do it yourself and actually where to find it. So I got this code from a really beautiful kind of way to learn kind of machine learning, way to learn to be a data scientist, which is called learnpytorch.io. It's pretty good. I liked it a lot. Not everything is freely available. It kind of has this nowadays this usual model where a certain amount is freely available, and if you want to have more, you need to pay. But what is freely available is already pretty good. And I just stole a little bit of code, and it's really nice. I like it a lot. The only flaw is that it's not for mathematicians, so there will be a lot of repetition somehow. In things you already know. But anyway, it's pretty good. So there's, for example, a 24-hour video available where they just really go through how to do it in code. So what I use is Google Colab. So Google Colab is again the same payment model. It's free unless you want to Google Colab. It's free unless you want to have better kind of access to GPUs or something. But everything I'm going to use and everything you probably will do in mathematics is usually okay to do it in Google Colab, so for free without paying for it. I guess I say it again, you can pay for it, and then you can get faster hardware, for example. Anyway, so the point is this PyTorch. So PyTorch is really cool. Python and Torch, PyTorch, um, is is built into the Google Colab, and it's like the main tool used when this time of recording 2024 to do machine learning. Yeah, it's pretty good. It's free. It's Python, and a lot of the things we discussed are actually already implemented, and you just need to load them. It's really really good. And yeah, so let me show you an example. Uh, the test here is just we're trying to use PyTorch to learn to find circles of two different radii. So to find circular, to kind of pattern in the circular data. And kind of another nice thing here is you can just import data sets and you can just play on them. And all I'm doing here is in the front is it's importing data sets. And what we have is essentially this picture. So the data set is two coordinates. That's the input. So our input layer has two coordinates. So whatever. That's just where they are. And the label, whether the circle is red or blue, and this is kind of the point. So you have blue circles in the middle and red circles on the outside. And I said again, so the input here in my data are x and y coordinates where the point is, and the output, the label for the data is we want to identify whether the data is actually a red dot or a blue dot. That's what it is all about. So two inputs, one output. And this is called a classification problem. So really just as before, we want to have a 0, 1, depending on whether it's whether it's red or blue, and we have 500 samples of each. That's what it is. And you split it into a test and a training set. So if you have 500 each, you have 1,000 in total. And well, we just split it 800 and 200. That's just it. And we have training sets for the x value and the y value. That's why there are four. Okay. And you can do all of this for free in PyTorch. So if you just go to this learnpytorch.io, they just have code that you can just copy and just get started. Yeah, and it is really simple. You can just build a model. Here's the model. So you just start it, and you just set up the layers. They are linear layers. So NN is neural network. Linear is linear. In is what type of vectors it takes, and out is what kind of vectors it returns. Here's another layer, 10, 10, and you always make sure, because matrix multiplication, this guy should be this guy should be this guy, and then one output. And we put in a nonlinear activation function, the ReLU, whatever, and then what you really get is layer. So here's the input. You apply layer 1 to it, you apply ReLU, you apply layer 1A to it. I could have called it layer 2, but anyway. You apply ReLU, and you apply layer 2, and then just return what happens. That is the whole neural network. That's it. And you can just do it in a few lines of code. And yeah, so it's called Circle Model V version 0, why not? And it has, as I said, 3 linear layers where it's the input and then 10 neurons in between with a bias, and it has a nonlinear value in the middle. And we'll see here now we'll see in a second what the value is actually doing. Okay, fine. And if you just run it just untrained it just has random entries in the matrices, so will get some random results. And here are the predictions. It's just really really different from what's going on. Anyway, so you always start with random inputs, so you get random results. Okay, you set up a loss function, depends a bit on your problem. So in this case, there's a certain loss function that you can use, and you set up an optimizer, which is the backwards step. And I just define here another kind of metric, which is called accuracy. You'll see in a second what it does. Anyway, so blah, 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 blah. So here is then the training step. So I let it run for 30,000 epochs. That's the repeat, 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 repeat. Yeah, and we do exactly what we said. We do the forward, we calculate the loss, and we do the backward. Just to be sure here, I like forward loss backward. This code splits it. So the learnpytorch.io splits it in 5 steps, which is fine. So for example, what I call backward here has 2 steps. But otherwise, it's really our forward pass. We evaluate the model on the training data, we get some predictions, and then we calculate the loss on the predictions compared to the training data or the accuracy, depending a bit what you want to do. And then there's built in the optimizer, which goes backward, the gradient descent that just goes backward. And you just build in, you can just use it as it is, and then you can just evaluate the model, and I will run it in a second again for you. But here you can see at epoch 0, it essentially is guessing, right? It's random, so it has accuracy like 50%. Yeah, it's essentially guessing. So this is on the test data, this is on the training data, and it trains on the training data and it tested on the test data. And as you can see, kind of the gradient descent, it will now try to minimize the loss function. So the loss function successively goes down and the accuracy goes up to it actually managed to get 100% of the results correct, which is kind of impressive. But anyway, in after the 17,000th iteration, it got up to 100% of the uh, of the things correct, which is pretty good. I will run it in a second for you, but for now, I read it before. And what it's really doing is, well, here's what it's doing. It's just output it on the train and the test data. So the function kind of created by the neural network is a piecewise linear function, which is a polygon. It's drawing a polygon. Here in this case, the polygon has that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. 10 edges. And yeah, so what did the old Greeks, probably the old Greeks, maybe even older, discover? Well, you can approximate a circle using a polygon. And this simple model just discovered the same fact itself without me telling it to do anything. It just started with random inputs and eventually it draws a polygon to distinguish those points. And the polygon is piecewise linear, and that's where you need the piecewise linear functions. Just for comparison, I did the same, kicking out, so there's just linear layers here, kicking out the piecewise linear one, and well, they did the same, and as you can see, it just learns nothing. It's still at guessing at the 18,000 epoch. Yeah, it still learns nothing. And why is that happening? Because now it's creating a linear function, but the linear function is a line in this case. With a line, you simply can't distinguish the two circles. And that's the real reason why you need piecewise linear maps. So you can draw nicer things. You can draw polygons instead of just linear maps. And I say it again, nobody here tells the computer what to do. It discovers that a circle can be approximated by a polygon itself, which is kind of the whole point. And it's a really simple program. And now imagine you have a little bit more complicated, you train it for a little bit longer, and you can just discover essentially any pattern. You should be able to rediscover all of mathematics just using machine learning. And eventually that will happen. And eventually, of course, nobody knows when that will happen. Obviously, I will not give you a date. It's happening at the 24th of August 2033. So there you go. If it's not happening then you can blame it on me. Anyway, so eventually that's just going to happen. It's just because the computer is just so much faster in doing it. In this case, it rediscovered that you can approximate a circle by a polygon just by itself, which is just really, really amazing. But anyway, let me just run it again. So I will rerun all, and we just see that happening live here. Run all. So it will rerun everything, it just sets up everything, takes a while. Eventually we go here, and it will redo the same step. And in general, it's completely random. I just set a random seed here so I get the same results. So kind of fun fact, computers can't really do random numbers. They can only do algorithms that pretend to be random. And if you set a random seed, you always get the same results. Kind of a fun thing to do. But in general, you shouldn't do that. I just do it for educational purposes. And the reason why you shouldn't do that, now it's going. So it starts off by guessing. Eventually, not really anything really happening here. Maybe it gets a bit better. So it takes a while to get going. Oh, 75.7. So it goes in the right direction here. 6.2. Excellent. 7.0. Perfect. 7.5. It goes in the right direction, right? So that's a gradient descent. You just do it all over again, just going one little step further. We're already at 98%, 99%. 99.62. We'll see where it goes. Ooh, it's already at 100% here. but it somehow doesn't really get much better. Here it got a little bit better, as you can see. So it takes a long time. So now it's already at 100%. And we'll see in a second that it will redo uh, the, where are they? That it will again rediscover the polygons. The really nice polygons here that it rediscovers. And yeah, the polygons are the way to separate um, the two patterns. And that's the whole point. So really, eventually, as I said, I would like to have a computer doing my work because I'm pretty useless, you know. And the computer can do it much, much better. Here discovered a polygon as an approximation of a circle for us, which is kind of cool and hopefully convinces you by now that you really need piecewise linear maps instead of linear maps. Yeah, so most data you get in life is not linear. So a line will not help you to do anything. Anyway, one more thing I need to say, this code is not designed to be efficient. You can be much more efficient with PyTorch. This code is more designed to be educational. So instead of setting up a neural network like step by step, you can just do it in one go if you want, for example. Anyway, I hope you enjoyed this video, and I also hope to see you next time.